Our last speaker of the day, Brad Mitchell, is going to talk something that to me, and I'm sure to a lot of folks, AI is something that over the last few years, there was certainly a huge bulge of concern that folks had over this, going back to Ezekiel Emanuel speaking at the ACR, and other stuff, and you know, maybe we're a little bit on the plateau or denouement of this, and I'm sure he can speak to this a whole lot better than me. He's now up in Charlotte, did his stuff at Emory, so he's sort of staying in the South despite the North and from Carolina.
Thank you, Joe. Thanks for the invitation, and thanks for suggesting this this topic. I'm dedicating this to my friend and colleague, Chris Ulrich. I'm going to sort of give a broad overview of AI today. I'm going to spend the most time sort of defining, explaining, and demystifying AI, because as it turns out, we'll see in a minute, how much you know depends on how afraid you are or how optimistic you are about the future of AI. So definitions. I don't have to tell you guys what intelligence is, but it's a broad capacity for learning, reasoning, understanding. So already we can see a little bit of a problem when we talk about artificial intelligence. The systems that we have in place now don't exhibit any of these features, right? You could argue learning, but certainly not reasoning or understanding. But it's defined as a computer method that performs tasks normally requiring human intelligence. You could argue that multiplying two numbers together requires human intelligence, but we've had calculators that could do that for decades, centuries. You can say it responds to stimulation consistent with traditional responses from humans, but that's kind of vague. I think you can already see artificial intelligence, maybe just a fancy word for advances in computing, as we'll see in a minute. But using that terminology, it's divided into two categories: narrow AI, which is everything that you've ever seen in practice or in the real world, all falls into this category of narrow AI. It has a narrow range of abilities. It's designed to perform only in one or a few well-defined domains, whereas artificial general intelligence is more the stuff of sci-fi, you know, a broad capacity to learn in brand new domains that it's never seen before. It raises, you know, philosophical questions like sentience and consciousness. And despite all the hype over the years, this is still, most people think, decades, if not centuries away from becoming a reality. So artificial intelligence, an application in AI is basically called a model or an algorithm. It's simply something that takes data as an input and runs it through some sort of mysterious black box and gives an output. The input could be plain numerical data. It could be an image. The output could be a classification like this. So in a lot of ways, it's exactly what we do day in and day out. And how we do it maybe is even more mysterious than how the AI does it. But Brad Pitt wants to know what's in the box, so let's see what's in the box. So how does a machine learn? So I think this example is really cool in illustrating what machine learning means and illustrating the fact that this is not a brand new concept, but it's what mathematicians have been sort of thinking about for decades. This mathematician, and this is from 1961, created a machine, and this is not an electric machine or even a mechanical machine. It's just a pile of matchboxes. And it's a machine that can learn how to play tic-tac-toe. Each matchbox corresponds to a possible state in which the board could be when it's your turn. And inside each matchbox are a collection of beads, say, of different colors, each color corresponding to where you could legally move in that situation. So as you play against the machine, it starts with just a random assortment of beads. When it's the machine's turn, you open up the corresponding box, randomly pull out a bead, and make that move. At the end of the game, if the machine lost, it's punished by not replacing those beads into the boxes. If it wins, it's rewarded by adding more beads of the color that was used. Maybe if it ties, you add a smaller number of beads, because in real tic-tac-toe, in optimal tic-tac-toe, tying is the best you can do, right? And it turns out that over time, the winning strategies will be sort of upregulated and the losing strategies will be eliminated. And after about 20 games, this thing was able to to tie him every time, which is optimal play. And so this isn't that we taught the machine the optimal strategy. We didn't even tell it what the objective of the game was, but it learned because this is machine learning exemplified. You can scale this up. If you use this method to play chess, you would need like, I think 10 to the 40th power matchboxes, which would just barely fit into our solar system before collapsing into a black hole. So as you can imagine, advances in computers have allowed us to actually implement these techniques. So there are a lot of different approaches to machine learning. Most of the ones that are in use now are basically statistical approaches. You'll see in a minute, this is just plain math. We're going to drill down to artificial neural networks, which represents the bulk of what has been put into use recently. And just for terminology's sake, when you see the term deep learning, it's practically the exact same thing, artificial neural network. You can use those interchangeably. And a convolutional neural network is a subset of this. We'll see what that means in a minute. So artificial networks, neural networks are so named because they have sort of a vague resemblance to what we know of as like synaptic networks in the brain. We have these nodes, which you could think of as neurons. They're connected by what you could think of as axons and dendrites, perhaps. I mean, that's sort of where the similarities end, but you can see why it gets this name. But what are these nodes? Every node is simply a mathematical function that takes a number of inputs and produces an output, which gets fed into the next layer. And what are the connections? They're simply weights and biases to strengthen or weaken how much a certain input corresponds to the next layer. So again, this is all just statistics. Let's look at an example. If you looked at a number of patients, you made an appointment in your imaging center. Let's say you asked the referring physician to just mark down a score of how severe the patient's symptoms are, right? If their symptoms are very mild, and then we measure whether the patient showed up for their appointment or not. So maybe the symptoms are very mild, they got better, they never showed up for the appointment. Maybe they're very severe and they ended up in the ER, and in the middle, they're likely to show up. Well, let's see if we can make a computer algorithm predict the no-show rate based on the symptom severity. So we create the world's most simplest neural network, just one input for the severity score, one output for the no-show probability or the show probability. Define some functions, and then the training algorithm basically assigns random numbers to all these connections. So at the start, you plug in a number and you're going to get a random output, and you're going to have about a 50-50 coin flip chance of predicting what the data shows. But what we do through a series of back propagation, as it's called, we start with the last term, we tweak it up or down to make the output more closely match what the data shows. We move back to the next layer, and the next layer, and the next layer, and then the algorithm will iterate this maybe hundreds of times, and eventually it will have optimal weights and biases so that if you plotted all the data inputs against the outputs, you would have a graph that you could use to predict the no-show rate. And this is a very simple example. I mean, this is something that statisticians have been doing for years, just with simple linear regression or logistic regression. But it's kind of the future, like C3PO saying, this is the odds of something occurring given given all the inputs, whether we want them to tell us the odds or not. But you can imagine, now you could, instead of just one piece of data, you could collect, their no-show history, what procedure it is, who's the referring physician, how far away do they live, what time of day is the appointment, so on and so forth. You could collect dozens of data points, and now you've got a very complicated data relationship that may be harder to work out with traditional methods, but the computer could create a really complicated neural network like this, and it only takes it a few seconds to iterate this once, and maybe a few minutes to find the optimal weights and biases for these different inputs to reliably predict the output. But what if your data set is much larger, like a single CT image is like 262,000 pixels, and each one of those pixels has to be fed into the network? What if your data is more complicated? You're not just interested in how one factor affects the outcome, but you're looking for a certain pattern, which could be anywhere in the image, whether it's left or right. It's the same to us, but strictly they're different, right? So for this, they've developed a technique called a convolutional layer, or which creates a convolutional neural network. What you do is, instead of generating just a weight and bias randomly, you generate a small image. This thing on the right is called a filter, and it's on the left, we're sort of changing examples. This is a picture of an O, and we're trying to get the computer to determine whether this is an X or an O, like harkening back to our tic-tac-toe example. So we create a random filter. In this case, it looks like a diagonal line, and then we compare it to like a subset of the image. We convolve them together. That's why it's called convolutional. And we get an output, in this case, the number 3, which means that it's a strong match. In fact, it's a perfect match. When we slide it over 1, we see that this is not so good of a match, so we get a low number. And after sliding it over the entire image, we create a feature map, and we can even sort of pool the sections together. And essentially, if you look here under where it says maps pooled, you've got just 4 numbers now. A 1 showing that this feature was detected in the top left corner and in the bottom right corner and not in the other places. So now we've got just 4 numbers that we can feed into the rest of our neural network. We started with a 36 pixel image. We've pared it down to 4 data points, but more importantly, we've detected something useful. We've detected a feature in the image. I'm going to change gears, and let's say that you're trying to detect the letter A. So the computer generates these little micro images randomly. One of them might look like the top of an A, one looks like the left or right side of an A. There may be hundreds of others which look nothing like an A, and those all get sort of down-regulated in the training output. But over time, you combine these in the neural network, and these connections will get strengthened so that if you have enough features matching what it thinks an A looks like, then it will call this an A. I'll put a star here because this could be important for questions later. But so the convolutional neural network has really allowed us to make a lot of strides in image classification, both across the world, but also in medicine. The advantage, as I mentioned, you can pare down your data and make it more manageable, but also you allow it to detect features, whether they exist in the corner or the other corner, or whether even they're partially obscured, like the third A you see there. We can tell that's an A, even though it doesn't have all the features of an A, but it has enough of the features that the computer will potentially classify it as an A. So it's very good at extracting features of the images rather than just sort of like, is this pixel bright or not? You won't be surprised to see that radiology and in neuroradiology, research and education on this topic has exploded recently. In 2019, RSNA started producing an entire journal just on the topic of AI. Even our own society has seen explosive growth, in fact, infinite growth. The ACR Data Science Institute has an AI section. They actually list all of the FDA-cleared radiology algorithms, which at current is 136. 52 of these are neuroradiology specific. This isn't all of AI that exists in our field, though, because this only obviously is tracking clinical applications, those that you would need FDA clearance for. It doesn't count, like, for example, if we had an algorithm for no-show rates, like I mentioned before, that's not here, because that's just a back office sort of thing. It also doesn't include homegrown algorithms, because if you have someone experienced in developing AI, you can make your own little project and answer a question with your own data. This isn't, but at least it shows the trend. So we've heard of the question like, will radiologists be replaced by AI? Well, actually, every industry is asking this question, or more likely, every industry is saying that another industry is going to fall prey to this, right? No one wants to think it's them, but let's see what the data shows. So this survey of medical students, 2/3 of them believed radiology was the specialty in medicine that was going to be most impacted by AI. And of those, like almost half of them, it caused them to be less enthusiastic about going into radiology because of that fear. On the other hand, here's another survey of 1,000 radiologists. They found they didn't just track what their perceptions of AI was, but also what their knowledge of AI was. And it turned out that the less you know about AI, the more fearful you are that it will be detrimental. And the more you know about AI, the more you have a positive attitude about it. So knowing is half the battle. So will AI replace radiologists? I like this quote from Dr. Lengholtz, who is a researcher at Stanford. He says, no, but radiologists who use AI will replace radiologists who don't. So I think it means that we should all be learning more about this, teaching our residents about this, medical students. It's something that can help us. I haven't got to the downsides yet. They are there, but I think for now, that's education is important. This is just sort of a broad overview of some of the applications I've, come across in neuroradiology. I'm going to group these into categories. The first is image classification. The ones with asterisks are among that list of FDA cleared algorithms I mentioned before. But you've probably all seen the ICH detection. You may have seen an LVO detection. We have both of these, I know, at Charlotte Radiology. Again, they're not perfect, right? But it's something that kind of gives you a glimpse into what's possible. Automatic aspects, right? Hyperdense vessel, different things like this. Brain tumor, glioma versus MET. There are a lot of things. Pseudoprogression versus progression. Wouldn't it be nice if they could do our thyroid rads for us, So that's image classification. That's kind of the big one. That's where all the people who think will be replaced by AI, because that's what they think is that's all we do is image classification, right? It is a big part of what we do, and it is something that there's sort of a defined path to how AI could get good at these tasks. But again, we're pretty far from that. And using it will really only help us in a lot of cases. The category of image segmentation, there was mentioned before of NeuroQuant, where the AI can detect different structures, calculate their volumes. It would be nice if you had a spine and it just popped up the levels for you. You didn't have to look for those yourself. Co-registration, like perhaps between a current and prior study, or between maybe a PET and MRI if they're not obtained simultaneously. Image optimization, that's a big one. So even if we're the ones interpreting the images, it's nice if we can improve the quality of the image. The top two images here are like an MP-RAGE type scan, done in 2 minutes and 30 seconds. You could sharpen it by, changing the parameters and making a longer scan, but then you introduce motion. But what if you could sharpen it without changing the scan time? So AI, has shown promise in this area. Same thing with lesion detection. Same thing with using lower doses of contrast and then sort of producing an image that's as if you had given the full dose. I mean, some of this is kind of hurts your brain a little bit, but these are things they're working on. Data analysis, so getting away from just images, but could we take data on how our radiologists are performing on the work list, or like when they click on studies, or how long they take to dictate, or how their reports change, and could this somehow detect physician burnout, for example? The surgeons, when they dictate their op notes, sometimes they say, this one took me much longer, it's a more complex study, right? Well, we use RVUs, which we all know are poor predictors of how long something will take or how complicated it is, but maybe the AI could look at your report and sort of add a modifier to the RVU based on complexity. These are things, again, this is not just my imagination, these are things that people have published. What about on helping us with our reports? Auto-complete the impression, give a suggestion for differential diagnosis, look for errors in our reports, left-right discrepancies, little typos or misspeaks or whatever it could maybe find those for us. Data mining. So I mentioned with like an image detection algorithm, let's say for intracranial hemorrhage, a good training model requires thousands of images that have to be hand classified by experts as whether they are positive or negative for hemorrhage. And that takes a lot of time. But what if you could go into your hacks and say, just give me the last 500,000 CTs, read the report, have the AI process the report and determine whether it's simply positive or negative based on its understanding of the report. So then in a few minutes, you've got 500,000 cases rather than 1,000 cases that took hours and hours to process by hand. Same thing with maybe research. Instead of saying, I searched the medical record for this term, what if somebody spelled it wrong, or what if somebody didn't use exactly that term? But if the AI, if you read the report, you would know whether they meant this is press or it's something else, right? Maybe the AI could help us with that and increase our data sets. And last, workflow optimization. This is one that's already in use, maybe work list prioritization, popping the positive studies or the studies that are more likely to be positive to the top of the list so they can be read, especially if it's an urgent finding. So now there are limitations and pitfalls here. The number one pitfall or limitation you'll find in machine learning is something called overfitting. Basically, the analogy is like if you watched one episode of Jeopardy over and over again and memorized all the answers, that doesn't mean you're like a trivia master now, right? Because if I give you the next episode, you're gonna bomb it, right? And so it's the same thing. It could get really good at. So most training programs have a test set and then like a validation set, or I should say a training set and a validation set of images. And so you're supposed to like, it'll kind of do both on each iteration, and you can see as it goes along, it's getting really good at the test set. That's the one it knows the answers to, but it's not really getting much better past a point at the validation set. I mean, this has analogies in how we learn as well. Like if you saw a dozen cases of press and they all looked like this, and then you saw these two cases, you might not call it press, but they are press. And so if you didn't have these examples in your training, then you wouldn't recognize it. So this can depend, like I said, on pathologic variations, but other things too, right? Anatomic variations. If you don't teach somebody that this basal ganglion mineralization is normal, they could call it hemorrhage, or the computer could call it hemorrhage. Sometimes we who have multiple vendors, that we read from, sometimes you can look at an image and say, oh, that's from this scanner, that's from that scanner. And for us, we know that that's just background. That doesn't matter to our diagnosis, but for the training algorithm, all it says is that if it only sees things from a Siemens scanner, and then you deploy it on a Philips scanner, it's going to be like, I don't know what this is. It's because what it's seeing is not what we're seeing. It is still kind of a black box. The way that, scan parameters, again, same thing. If it was trained on like standard FLAIR images, and then you start giving it like radial or synthetic flares, it may not know what to do. Even location and as a subset of that, patient demographics. This is well demonstrated in the literature. An algorithm was trained on a predominantly white population, and then when you take it to another place that has a predominantly Black or Asian population, it doesn't do it as well. The last thing we want is racist AI algorithms, right? So, the thing is that like we can quiz our residents and find out why they think this is their diagnosis, but the AI in most cases can't really tell us how it came to this conclusion. Just somehow it found some feature that mapped A to B. There's like a famous example in the literature of like, teaching maybe an algorithm to detect TB on an X-ray. And then it turned out, like they realized after a while, when it was really good at the training data and really bad in the real world, that there was like a little marker in the corner that said this image is from the TB clinic. And so it just called all those TB, and all the ones that didn't have that, not TB. That doesn't work in the real world, right? So this is kind of like, it's not always clear how or why this occurs. In other words, what we want it to do is identify imaging findings. What it actually does is just find some random shortcut to the right answer. So, so what are the solutions to this? Like, we need to increase the diversity of training examples, or we need to at least have training examples that match the location where it's going to be deployed. This is something that it's like part of the promise of AI. Think about like the bone age films. This was the RSNA AI competition, I think 3 years ago, was to have the AI give a bone age for hand films. But like, there's so many different types of people in the world, and they have different, genetic, different maybe nutrition available to them, and their bone ages are not going to all be valid. So what if you could take this algorithm and just train it on your local population and have it be really good at taking care of your patients? So having a data set that matches where it's going to be deployed makes a lot of sense. And then like, when you got to be careful when you're constructing your data sets. Don't take your patients and let them be in both data sets, because it's kind of like leaking some of your Jeopardy questions into the next episode. You'll know those, but not because you know it, just because you saw it before. There are things you can do as well, like this graph kind of shows on the top the error will come down in the validation set, but it actually can go up even at the end when you're fitted too well to the test data. And you can do methods like early stopping. This is my last slide, but there are other limitations too, like do we want the AI to use ancillary data when classifying an image? Like maybe it's useful for it to know that this came from the MS clinic, or maybe it's not useful. Like, but whether that happens or not will determine how well it gives the right answer. Automation bias is a problem because if the AI looks at the image first and then you are over reading it, basically, if it calls it negative, are you going to spend less time and just say, well, it's probably negative? If you do, then you're kind of creating a self-fulfilling prophecy. If you never find anything the AI missed, then you're obviously replaceable, right? So there's a problem with that too. The people on the other end might say, well, the AI called it normal, I won't wait for the radiologist report. So that's another problem. Even the work list prioritization, if it deprioritizes what it thinks is negative, like at the top of the list, it's putting like the most obvious hemorrhage, which anyone could see, but now we're delaying reading the other cases that might be more subtle. So that's something to watch out for. And really, if all your training is based on human classification, then the AI can only be as good as the human classifiers, right? So in a way, there's a cap unless you find other ways to do it, like to map them to actual, clinical or pathologic diagnosis, but that's not always possible. That's it. Here are a couple of links to learn more, and hopefully we won't be taken over anytime soon. I could be wrong, but we'll see.
That paper was